So you're in class and you're thinking, I'm just here because I need a math credit, but this stuff is never going to show up again in my life, is it? And your teacher, being able to read your thoughts, is like, well, it shows up all the time in physics. And you're like, but physics is going to do its thing whether I know how it works or not. And she's like, well, rate of change is also very useful for economists who, and you give her this look like, you seriously think I'm going to be an economist? And you're thinking to yourself, yeah, see, may as well be spending my time playing video games. But you forget she can read your thoughts, and so she goes, well, your video games are only fun because someone modeled physics in them. And in that moment you realize two things. You will never be able to mindlessly enjoy video games without inadvertently appreciating the math behind them. And your math teacher is a psychic who totally knows you have a crush on Jessica. So now you, dear viewer, are thinking, well, how much longer is this video? Well, I haven't even gotten started. Here's an example of physics for you, but that's too complicated. So here's another one, but that's too complicated. Here's a good one, Angry Birds. Of course, we can't concern ourselves with the forces behind the bird in the slingshot, or air resistance, or momentum transfers and impact, or torque, so we're going to simplify things a bit. Alright, so here's your bird. Let's say you can control his initial velocity and the angle at which you launch him. He travels at a constant rate. Okay, so clearly he's not going to go in a straight line, but how do you keep track of where he's going to move? And yes, vectors. You thought you left those behind in pre-calc, didn't you? So let's split this up into velocity on the x and y axes, because that's the plane he'll be traveling on. Sometimes he travels on JetBlue, but usually xy. But wait, how do we know the size of these components? Well, slide the Vy over here, and oh look! A right triangle. Do some trigonometry like so, and Vy is V sine theta, and Vx is V cosine theta, because this is that over that, so we get this by itself, we multiply by this and this. So now we have velocity, but we want to know position, because we want to see how far we can throw this guy. And just to mix things up, let's say the peg is below the slingshot, because if he's on the same level, the answer is always 45 degrees. So to do that, we're going to have to do a little integration, which in this case isn't very hard. X position equals Vx times time, or Vxt. Y is a little trickier because we have to account for gravity. So, A equals G, V equals Vy minus Gt, Y equals Vyt minus Gt squared over 2, differentiation backwards, bish bash bosh. Except we started above the ground, so Y equals negative Gt squared over 2 plus Vyt plus H. What we want to do here is figure out the horizontal distance x. We know Vx is V cosine theta, so we need to solve for t, but we don't know x, so there really isn't anything meaningful we can do here. But we can use our formula for y because we know Vy and g and h, and we know that at the time the bird hits the target, y is going to be equal to 0. Or, if the target isn't on the ground, you can just replace h with h minus your ending height, so y can still be equal to 0. So we've got negative gt squared over 2 plus vyt plus h equals 0, which is a nice quadratic equation, and we can solve for t that way. So t equals v sine theta plus square root v squared sine squared theta plus 2gh all over g. Plug in t to the equation for range x, and we get x equals v cosine theta divided by g times v sine theta plus square root v squared sine squared theta plus 2gh. So, just for the halibut, let's figure out what angle gives us the greatest range. The derivative in respect to theta gives us this beautiful looking equation. From here, to find a zero, we can put the whole thing through Newton's method, or, since that's arduous and we only really use Newton's method on a calculator anyway, we can cut out the middleman and just graph the darn thing. Using some numbers from this handy-dandy website, we now have the height of the slingshot, the initial velocity of the bird, as well as the acceleration due to gravity. So we can see that for optimal results, we should launch our bird at about 0.74 radians, or 42 degrees. Now, Angry Birds has a lot of obstacles in the way of seeing how far we can toss the bird. This simulator is pretty good at giving a visual demonstration. Congratulations, you are a real entry-level physics student.